Continue. Worksheet 16A, combine loading. For the shaft, we already did and find out the external reactions at the fixed end and the internal forces at A. The two only meaningful thing that we consider. First is the internal normal force, which is 50 kips, and that, as you can see, that is the normal force. So let me down here, that is actually the normal force NA. And then we have the torsion TA about A, negative 40 inch kip. Negative just stand for it opposite to your the right hand rule, which is rotation about x-axis, the longitudinal axis. So the next step, based on the step here, let's go to review. Internal forces, now stresses with you the super position to find out. So as you can see now, let's go to the next step, which is the stresses at A. Stresses A. So what do we have? As you can see, Ix will create the normal stress at A, because that go back to similar to the note that we have here, that a P, internal normal force P, and will create the normal stress which is perpendicular to the surface, and that is sigma x. So from that, as you can see, we have sigma x equal to P over A, that equation, and in this case, as you can see, it equal to NA or Rx, right, over the areas, and that we have, that is 50, and if the normal force go out of the section, so it creates the tension 5, radius 2 inches for the radius, so pi r square, so you have that pi 2 square, and from that we have that 3.98 and kips over inches square, so it will have KSI and intention. M tension. And then the next is the stress, right? The stress for due to the torsion TA, and as you already know, the torsion will create the shear stress. Okay, T rho over J. So let's go back to here. Tau xy equal to 0 over J. And from that we can plug in T 40 inch kip. So 40 times rho, either A, as you can see, A is outermost fiber on the top of the shaft, so it will be equal to the radius, so it will be 2 inches divided by polar moment of inertia, so pi over 2, that is go to the back of your books, inside cover of your textbooks. And if you are not sure, go back to review in the torsion class. So that is pi over 2 radius power 4, and from that we get this number is 3.18, and also KSI. Okay, then when we have stress, that is the question asked, and they are not done yet. They also ask us to determine the state of stress at point A that we have, and then find on of that and draw the 2D state of stress block or 3D stress cube and label the stresses at A. So let me start with the cube and then we elaborate with the a set of 2D stress block. A set, it means more than one stress block because this is 3D problem as you can see here. So at A with the cube AB XYZ in that order, so we can draw the XYZ component. So we have a cube like that. A cube. Look like okay cube, right? And then we have the axis based on the definition XYZ. So you have that will be Y, that will be Z, X, that will be X. And that will be Z. So from that what we have sigma X because that is the normal stress in X direction because that force AX as you can see go out of the plane X, plane divided by the axis perpendicular to it. So you can the cut through A, we have that here, that plane. So in this case you have the sigma X, it actually that go from plane parallel to the x-axis. So let's make it parallel, perfectly parallel here. So X, so we have perpendicular to the x-plane, parallel to the axis. So that one is equal to 3.98 KSI, which is sigma X. And of course, the opposite will be true for 3.98 KSI. And then you have tau xy. So if you recall, X stands for the plane that the tau, the shear stress tangent to, and Y is the direction. So the plane, positive X plane, as you can see here. Let me make a note here. You have this is the positive X plane, and this one is positive Y plane, and the other opposite it will be negative plane because plane divided by the axis perpendicular to it, as you can see here. So I try to do this problem very slowly, so hopefully you got it. So the top plane in here, so that is the positive Z plane. Okay, so that's how it defined. So tau xy, as you can see with the torsion at T of mx, what we draw here is the positive, but it opposite, it negative, so it opposite direction. So as you can see, the shear at this point at A, it will be like that, tau xy, right? Tau xy. So with that, we erase that, make it not confused. So go back here, redraw this. So go back. So tau xy, it means it on the x plane. So it's the x plane I already defined and in y direction. And in this case, as you can see, I just show you it go to the positive y axis. So it will be on the positive x plane. So that one, the tau xy should be here. And that tau xy actually is 3.18 KSI. And of course, the opposite is true on the negative x plane, that also 3.81. And of course, on the y plane, it's also tau yx. So that also the same. And then we have the other negative y plane, also tau yx. So all of that we already done for the cube, right? So that one we consider that is we consider that one is the 3D stress cube. Let's write down here 3D stress cube. And now we want to draw out the a set of XYZ, the set of 2D stress blocks. So from that one, we can draw out the block on the XY direction, YZ direction, and also XZ. Okay, so that can elaborate into three 2D stress block. The first one here, and I just follow the direction that we have it similar in the identify XY. So from that we can have X that way, and of course Y going down based on the definition. So basically I look at from the top of the sub and I see XY and just draw that way. And then we also have another block which is XZ, YZ, okay, YZ first, and then YZ. Of course, you can do XZ, and then YZ. So let's put the XZ, so X that way. So you don't have to be follow the order, and Z, XZ. So I look at from the positive Y, look down, so you have that. And then we have a YZ. So we have another stat block here, YZ. So this is YZ, and this is Y. So how is stress block look like? So as you can see, for the XY we already have sigma X and tau XY. So we have this case, as you can see now, in X. So 3.98 KSI. Okay, so of course that one also 3.98 KSI, the positive plane on the left for this one based on my show the positive x-axis to the left. And tau xy, as you can see, positive 3.18 on the positive x-plane and follow y-axis. So this in the positive x-plane, it have to going down to show that it follow positive y-axis, because positive, and it's same at the 3D cube as you can see here. Tau xy also follow the positive y-axis on the positive x-plane. So that one is 3.18 KSI. And when you have that, you can opposite on the negative x-plane. And of course, it have to rotate differently clockwise on the y-plane, so that it make it equilibrium. So that what we have for xy. And now xz. So in x, so x-plane is still have the normal sigma x, and that is 3.98 KSI. We don't have the tau x z, so it's nothing. We don't show it. We don't have sigma z, so nothing. We don't show it. And it's showing here. You can see have nothing on the z plane. And then it yz. Do we have sigma on y direction? No, only sigma x. Do we have tau yz or zy? No. So that is nothing on the 2D stress block in YZ direction. So that one I make that is a set of 2D stress blocks. Okay, so from that we can use the Mohr circle, which is the next problem that they show us here. The next part, draw the Mohr circle for stresses in XY plane. XY plane, we already have XY plane there. So we have just go ahead to find out on of the radius and the right center, right? So Mohr circle. So we have radius r equal to square root of sigma x over 2. So 3.98 over 2 square plus tau xy square, 3.18 square. So from that we have 3.75 KSI. And we have tau max, of course, that is also equal to tau max. And we have sigma 1, sigma 2, and sigma average, right? So that sigma average equal to 3.98 over 2, and that equal to 1.99 KSI. So from that we can draw the Mohr circle very quickly here. So you see tau, KSI, sigma, KSI, and sigma average, that is 1.99. So let's put it about 2, as you can see. So you have the center here. Okay, and in y-axis, no sigma y, so it have to be first find out tau max. Tau max also 3.75. So that is the radius. So that is tau max. And from that we can draw the Mohr circle. Hopefully we can draw a good Mohr circle here. Circle. Look good on the first half. Look also good on the second half. And that one we can find out this is actually sigma 2, sigma 1, and from that we can find out sigma 1 equal to sigma average plus radius tau max, right? So it equal to 1.99, so at 3.75, so 5.74 KSI. And sigma 2 equal to sigma average minus the radius, which is tau max, and that is negative 1.76 KSI, which is same as we did in the Mohr circle. And where is the x plane and y plane? X plane is, as you can see, positive x plane is 3.98 KSI for sigma, and the on the left, that is the positive x plane, and that create what? Counterclockwise. The tau xy create counterclockwise for the block. When it counterclockwise on the Mohr circle, it is negative. So we have that is 3.18. Tau max here 3.75 KSI. So 3.1 is the x plane that you have it here, which is 3.98. So that is the x plane, and it's 3.98, and then negative 3.18 KSI. And of course we draw that through the center. It will meet at this point, and because sigma y is 0, it have to be on that point, so it will be y equal to 0, positive 3.18 KSI, and that is y-axis. And with that we done just put sigma average here, as you can see, and that is 1.99, and we done for this problem in there. So you just at the sample how to draw the 3D stress group and a set of 2 stress blocks, and you can be able to practice in the next 2 problem, 16A, 16B, and 16C.